Hello everyone, thank you very much for joining the presentation. My name is Hao Yang and I'm currently an assistant professor at McMaster University in Canada. In the presentation today, I will introduce the development of the centralized non-recurrent queue management system, and this system is designed to mitigate the congestion caused by the freeway non-recurrent queues. This is actually in a joint work conducted by McMaster University and Toyota North America. Here's the contents of this presentation. At first, I will make a brief introduction about the research background, including the statement of the problem and some of the existing research work. And then I will show the details about the system development. After that, I will propose a detailed evaluation about the system, including its mobility and safety benefit and the social impact analysis. Finally, I will summarize the findings in this research and list some future recommendations. In this research, we will try to solve the congestion caused by non-recurrent queues. Actually, the non-recurrent queue is quite common in reality on freeways due to the errors of the human drivers, such as the distractions or the collisions. The vehicles can move slowly or even stop on the road, and then they will partially block the lanes. In that sense, the other vehicles behind the slow or the stopping vehicles will be forced to slow down or even stuck in the queue. Due to the huge speed difference between the queued vehicles and the adjacent lane, these vehicles cannot make a lane change to leave the queue, and these behaviors will result in a very huge travel time delay for the queued vehicles, and this will further increase the length of the non-recurrent queue. With that, we will observe the increased congestion levels for the entire road segment. In the literature, there are a lot of systems proposed to solve road congestion. Variable match sign is one popular method. It's able to display road incident or construction information in real time for all road users. However, due to the high installation and maintenance costs, the coverage of the signs will be very small, and they are not able to handle non-recurrent queue, as the queue can happen at any time and any location on roads. Recently, with the development of the connected vehicles, the individual drivers can receive the personalized in-vehicle variable speed limit in real time, and this speed limit will help the vehicles to control their speed and reduce the downstream traffic congestion. Some of the vehicles can even receive the lane changing instructions to maintain a high speed on the road and avoid the downstream slow vehicles. However, most of the connected vehicle applications does not consider the lane differences. In that sense, they were unable to solve the congestion caused by the non-recurrent queue. One pioneer research was conducted by our previous research. In the previous research, we developed a distributed non-recurrent queue management system with the help of the connected vehicles. And this system will utilize the connected vehicles to monitor the speed at different lanes, and then they will control the speed of each individual vehicle to help the queued vehicle leave the non-recurrent queue faster. However, in this system, each connected vehicle will search for the optimal instructions by themselves without any coordination. In that sense, if there are a lot of connected vehicles on the road, the system can even increase the congestion levels of the entire road. In order to overcome the drawback of the distributed control system, in this research we will propose a centralized non-recurrent queue management system, and this system will mitigate the congestion caused by the non-recurrent queue. In the meanwhile, we will also maintain high system benefit at a high market penetration rate of the connected vehicles. In the system development, we're going to use the connected vehicles to monitor the road traffic conditions and detect the non-recurrent queues. Also, we will use this information to predict the impact of the non-recurrent queue on road congestion. In addition, we will control the speed and the lane of the connected vehicles so that they can avoid the congestion and help the queued vehicles to leave the congested lane. The system actually has two components: a cooperative non-recurrent queue management system to mitigate the non-recurrent queue efficiently, and a centralized lane changing assistance system to prevent the propagation of the road congestion. The first component, the cooperative non-recurrent queue management system, is proposed to assist the vehicle in the non-recurrent queue to complete lane changing faster, so that we can reduce the congestion impact of the non-recurrent queues. The core idea here is to utilize the game theoretical lane changing model to coordinate the behaviors of the connected vehicle in the adjacent lane and the queued vehicles. The control can be categorized into two scenarios. And the first one, if there's any queued connected vehicle forcing the gap ahead of the connected vehicle in the adjacent lane, we will use the game theoretical lane changing model to search for the optimal speed instruction for the connected vehicles in the adjacent lane. The equation here shows the objective function of the optimization problem, and it's applied to maximize the probability of the queued vehicle to complete lane changing successful and maintain the high speed of the connected vehicle. In the second scenario, if there's a queued connected vehicle ahead of the connected vehicle in the adjacent lane, we will try to coordinate the speed of these two vehicles, and the speed will be adjusted to maximize the probability of the queued connected vehicle to complete the lane changing behaviors. And the equation here shows the estimation of the speed instruction for the connected vehicle in the adjacent lane. The second component, centralized lane changing assistance system, is designed to assist connected vehicles to avoid the downstream road congestion at all different market penetration rate of the connected vehicles. The figure and the equation here shows the development of the system. Basically, we're going to use the connected vehicles to monitor the traffic condition at different lanes, and then apply the model predictive control to search for the optimal lane instructions for each connected vehicle. And the optimal lane is selected to balance the traffic at the different lanes so that they can maximize the speed of the vehicles on all lanes. With this control, the connected vehicles can receive the optimal lane to gain the highest mobility, and now the lanes will be congested at different market penetration rates, even at a very high percentage of the connected vehicles. Finally, the centralized non-recurrent queue management system will be developed by integrating the cooperative NRQM system and the centralized LCA system. The figure below shows the integration of these two components. Basically, the road will be divided into two regions, NRQM control region and the LCA control region. The NRQM control region will start from the head of the non-recurrent queue to a fixed distance behind the tail of the queue. And the LCA control region is set immediately at upstream of the non-recurrent queue control region. For any connected vehicles in the LCA control region, it will receive the lane changing instructions and change to the optimal lane with the high speed. Also, once the vehicle enters the NRQM control region, it will receive the advisory speed instruction to help the vehicles in the non-recurrent queue to complete lane changing faster. With this integration, the connected vehicles will always maintain a high mobility, and it will also help to reduce the congestions caused by the non-recurrent queue, even at a very high market penetration rate of the connected vehicles. In this research, we conduct several Emerson simulations to evaluate the performance of the proposed centralized NRQM system. The figure here shows the geometry of the network we simulated. Basically, it's in the freeway segment with one on-ramp. The flow is set as 5,000 vehicles per hour on the mainland freeway and 500 vehicles per hour on the ramp. We also model two slow vehicles where the speed will be set as 2 km per hour at the slow region. The centralized control system is also applied in the simulation. We evaluate the mobility and safety benefits of the proposed system under different market penetration rate of the connected vehicles. The figure here shows the savings in the travel time delay under different market penetration rate for connected vehicles and non-connected vehicles. Basically, we can see that the centralized system can improve the mobility of both connected vehicles and non-connected vehicles. And at a higher market penetration rate of the connected vehicles, the mobility benefit would be larger. In addition, we will observe that even with only 10% of the connected vehicles, the travel time delay for all the vehicles can be reduced significantly. In addition to the mobility benefits, we also observed a higher safety improvement for the connected vehicles at a higher market penetration rate of the connected vehicles, and the improvement of the non-connected vehicles will also be very significant at all different penetration rates. In addition to the average performance of the connected and non-connected vehicles at different market penetration rates, we also evaluated the fairness of the system to the connected and non-connected vehicles with different departure time. These two figures compares the performance of the connected and non-connected vehicles among three different strategies: the base scenario without control, the distributed control, and the centralized non-recurrent queue management system. From the figures, we can observe that At the market penetration rate of 20%, where the penetration rate is low, the centralized system can significantly improve the mobility of both connected and non-connected vehicles at different departure times, while the performance of the distributed and centralized control are very similar to each other. This indicates that the low penetration rate will result in the very similar performance for the distributed and centralized system. However, the result at a high market penetration rate will be very different. These two figures compares the travel time delay for different types of vehicles under different departure time with the base, distributed, and centralized control at MPR equal to 80%. From the figures, we can see that even at a very high market penetration rate, the centralized non-recurrent queue management system can still maintain a very high mobility savings for all vehicles at all different departure times. However, the distributed control has a much worse performance at a high MPRs. It will also significantly reduce the mobility of the connected vehicles, and sometimes it can make it even worse compared with the base case. In reality, we know that different automakers will apply different connected vehicle applications for their own auto modes. In that sense, it's very important for us to evaluate the performance of connected vehicle applications under mixed control environment. In this research, we designed two scenarios, competition and non-competition for Toyota and GM vehicles. Under the competition scenario, the Toyota vehicles will deploy the distributed NRQM system, and the GM cars will apply the distributed LCA system. While in the non-competition scenario, the Toyota vehicles will use the centralized NRQM system to accommodate the GM cars with the distributed LCA system. In these slides, you will observe two tables which will compare the travel time delay under low and high penetration rates of the connected and the non-connected vehicles. The connected vehicles will be referred as the Toyota and GM vehicles. And from the comparison, we can see that at the low MPRs, the centralized system can slightly reduce the mobility of the Toyota cars, while overall, the mobility of all the vehicles can be increased by the improved mobility of the non-connected vehicles. While at the high MPRs, the centralized system under the non-competition scenario can significantly improve the mobility of all different vehicles. In addition, we also evaluated the performance of the proposed centralized system under high congestion level. In this example, we doubled the traffic flow in the simulated network. The two tables here compares the travel time delay with low and high market penetration rate under the high congestion level. Basically, we can see that with a high congestion level, the mobility benefit of the centralized system will be reduced. While for the low penetration rate, we will observe very similar performance for the competition and non-competition scenarios, but with the high penetration rate of the Toyota and GM vehicles, the mobility benefit from the non-competition scenario will be more significant compared with the competition scenario. And this verifies the benefit of the centralized system at a high penetration rate and a high congestion level. So that's all about the work in this paper. Basically, in this research, we developed a centralized non-recurrent queue management system to improve the mobility and the safety of the road traffic with non-recurrent queues. And from the study, we found that the system can reduce the travel time delay by up to 85% for both connected and non-connected vehicles. Also, they are able to improve the driving safety by 70% for connected vehicles and 50% for non-connected vehicles. The system is especially designed to improve the road performance at the high market penetration rate of the connected vehicles and high congestion levels. However, in this work, we only evaluate the system under a very simple road network. In the future, we will conduct a more comprehensive analysis about the system in the large-scale road network with various non-recurrent queues. We will also conduct a sensitivity analysis about the centralized system to find out the optimal settings of the system and gain the best performance of the system. Finally, we will design a small-scale field experiment to understand its real-world benefit. So that's all about the presentation. Thank you very much for your attention. Please feel free to send me email if you have any questions.